All right, let's do these graphs here. So in number 8 here, we've got a car that's driving at 16 meters a second when the driver hits the brakes, slowing at 3 meters a second for 4 seconds. So that's sort of the first chunk of this, right? Because then what happens, so here he's accelerating, right? He's got an acceleration. Acceleration, all right? Excuse me. And then there's a second chunk of this in which he maintains a constant velocity for 6 more seconds. So there we've got a constant velocity. All right, so what we want to do here is do exactly that, break it up into chunks. All right, so in chunk number 1, here are the things that we know. We know that the initial velocity of the car is 16 meters a second. We know that the car is going to slow at 3 meters per second squared. That means the velocity is going to decrease. So I've got to make that acceleration negative. Again, that is a huge, huge issue with students forgetting to put in those negative signs. So try to remember that. All right? And then all of this takes place over 4 seconds. All right? And then here it says assume the position begins at 0. So we can assume that our starting position is 0. So to finish this guy, we need to figure out what VF is, we need to figure out what displacement is, and we need to figure out what our final position is. So I should put an arrow over my D here. All right, so final position, we can use the ax, that's VI plus A times T. We've got our VI, we've got our A, we've got our T, plugging in numbers, and we end up getting 4 meters per second. Notice it's still positive, so the car is still moving forward. It shouldn't be too surprising. Since, you know, it's a car hitting the brakes. You don't go backwards when you hit the brakes. Let's see, our displacement is going to be 1/2 VF plus VI times the time. So now we know our VF, our VI, and our time. So we're going to get 40 meters. And if we started at a position of 0 and then went forward 40 meters, that means our final position is going to be 40 meters. Okay? So those are all of the calculations for this chunk at the beginning where he's accelerating. Okay? So let me free up some space on, whoops, hit it again. Holy cow. All right, so we freed up a little space. So now let's do the second chunk, chunk number 2, where he's going at a constant velocity. So now what we know is he kept his velocity. Well, what is that velocity? Well, it's going to be whatever he ended up at the end of the last chunk. So it's going to be 4 meters a second. And it tells us he does that for 6 more seconds. Since his velocity is constant, I can use my constant velocity equation, which tells me that my displacement is velocity times time. So 4 meters a second. For 6 seconds, we're going to go 24 meters. Now, where did chunk 2 begin? Well, that began wherever chunk number 1 ended. So here, my starting position for chunk 2 is 40 meters. And then I'm going to go another 24 meters, which means my final position will be 24 meters. No, it won't. Try that again. 40 plus 24, oops. 40 plus 24 gives you 64 meters. All right, so let's once again buy ourselves a little bit of room on the board here. Oops. Okay, so now we can do this, right? So we've got a total of 10 seconds, right? 4 seconds here, and another 6 seconds over here. So all of these axes on the bottom are going to be time. So 0, 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10. And then our, I always say to do the velocity graph first. So velocity measured in meters per second. So let's say our velocity has to include everything. It's always positive, so we got to get up to positive 16. So let's just go by 2's. So we'll go 2, 4, 6, 8, 10, 12, 14, 16. So in chunk 1, our starting velocity is 16. Right there, sort of. I need to calibrate my board, it looks like. The final velocity was 4, and that happens at the end of 4 seconds. For 4 seconds, my velocity is 4. There's chunk number 1. You know what? Let me do this. Here's chunk number 1. We'll do it in red. Keep up with the color coding that we used at the beginning. So there's chunk number 1. Excuse me. All right, and then in chunk 2, his velocity just stays at 4. So his velocity just stays at 4. All right. Let's go over here and do the acceleration graph. That was easier than position. So acceleration, meters per second squared. So our acceleration in the first chunk is -3, and our acceleration in the second chunk, oh, I didn't write it down. Well, to find this acceleration, you can either use Vf minus Vi over t, but I haven't written down my Vf and my Vi. Well, why not? Well, my velocity is constant. So both my Vf and my Vi are going to be 4. So I'm going to end up with 4 minus 4 divided by time. The acceleration is 0, but we knew that because the velocity is constant. So your velocity is not changing. All right. So over here, I need to find a spot to put an acceleration of 0. And then we'll go -1, -2, -3. So for the first 4 seconds, my acceleration is -3. And then for the last 6 seconds, the velocity is 0. Or acceleration is 0, sorry. Acceleration is -3, and then acceleration is 0. All right, and finally, position time graph. So our position needs to get all the way up to 64. We got 10 boxes, so I'm going to number by 8. So we'll go 0, 16, 24, 32. What did I do? That's not at all right. Let's try that again. So I was going to number by 0, 8, 16, 24, 32. This looks better. 40, 48. 56, 64, and that's as high as I need to go. Okay, cool. So let's plot our points. So we began at a position of 0, and at the end of chunk 1, which was 4 seconds, our position was 40. Looks like it's going to live right about there. And then chunk 2, we go from 40 to 64. So chunk 2, the velocity is constant. So I'm just going to draw in my straight line to connect those guys. Okay. Chunk 1, though, the velocity is not constant. So we have to decide which of these two things is happening. Is it doing this, or is it doing this? Oops. All right. So is it doing that first dotted line, or is it doing the second dotted line? All right. Well, there's a couple ways of knowing it. I guess the easiest way, or the way I'd like you to be doing it, is to be thinking about what's happening to the speed. Is my object speeding up or slowing down? Since we're hitting the brakes, that means we're slowing down. The velocity is going from 16 to 4. Okay, so we're slowing down. That means the graph needs to get less steep. So it's got to start out steep and then get less steep. Okay? Make it any better. But, okay, so there's our final graph. Let's get rid of this dotted line here. Remember. All right, there we go. So that is our graph for number 8. All right, number 9. This one's actually fairly similar. We again are going to have 2 chunks. So it says ball rolls at a constant velocity of 12 meters a second for 2 seconds. So there's our first chunk. Constant velocity. At this point, it encounters a hill, which causes the ball to slow down, stop, and roll back down. It says the ball is on the ramp for a total of 8 seconds. And during that time, it's going to be accelerating. So that's going to be our chunk 2. All right, and then it says assume the bottom of the ramp is a position of 0. All right, so let's see what we can do. Let's write down some stuff for chunk number 1. So for chunk 1, I know that my velocity is 12 meters a second, and it's constant. I know that this is going to happen for 2 seconds. And I know that at the end of these 2 seconds, I'm going to be at the bottom of the ramp. And remember, the bottom of the ramp is a position of 0. So I know at the end of those 2 seconds, my final position is 0. And since my velocity is constant, I know my acceleration is 0. I can find my displacement, since my velocity is constant, by just using distance equals rate times time, velocity times time. So 12 times 2, that's going to give me 24 meters. So let's think about this. If I ended at a position 0 after going forward 24 meters, my starting position must have been negative 24 meters. Okay? So that's everything for chunk number 1. Right, so, man, every time. Okay, so let's try that again. Alright, there we go. So there's our first chunk. Now, in chunk 2, we're on the ramp. So there's a little bit more going on. So what do we know about chunk 2? Not a whole lot. It tells us we're going for 8 seconds. But we just figured out a whole bunch of stuff. For example, we know that when we get to the ramp, we're still going 12 meters a second. And I also know that the starting position when you get to the ramp is 0. Let's see. It doesn't give us much else to go on. So let's make a little drawing here and see if we can figure out what's going on. So here's our ball at time equals, well, 2 seconds have elapsed total. Maybe I should be, no, that'll overcomplicate things. All right, so we'll just leave it at that. So when you're at the bottom of the ramp, the velocity is 12, and I know it's going to go up the hill and come down the hill. That's going to take a total of 8 seconds. Oh, I know the velocity here, don't I? Remember, the path is symmetrical, so the velocity at the end of those 8 seconds is going to be negative 12 meters a second. Ah, now I have something to go on. Because now I can use a screwdriver to find my displacement. Alright. And when you do that, look what happens. My VF and my VI, one of them is positive 12, the other one's negative 12. We end up getting 0 for displacement. Oh, well, that makes sense, because like I just said, the ball's going to go up the hill and come back down. It's going to be back at its starting point. Oh, that means I need to figure out what's going on here when we're at the top of the hill. All right? So, we've got sort of a sub-chunk, right? We want to figure out what goes on here. All right? So we'll call that chunk, I don't know, 2A, I guess. All right? So let me get all this garbage out of the way. Okay, so for that chunk, here's what we know. We know that our initial velocity is 12 meters a second. We know, oh shoot, I forgot to do something in chunk 2. I guess it doesn't matter. So how long does it take to get to this point? The time to get here is going to be half of the time it took to go up and down. So that's going to be 4 seconds, right? And then our final velocity is 0, right? Because it's got to stop up here at this point at the top. So, let me clear off a little more space. We can use this now to find our acceleration. I know all my numbers, so I'm going to get negative 3 meters a second squared. And that's actually going to be for all of chunk 2, right? Because the entire time it's on the hill, that's going to be the acceleration. Right? And now I can find my displacement while it's on the ramp, which is going to be screwdriver x. Nope. Watch out for the difference between the xf and vf. People, myself included, occasionally mix those up. So plug in your numbers. So my average velocity is going to be 6 times 4. So this gives me 24 meters again, just by weird coincidence. Okay. So, and if the bottom of the ramp was a position of 0, that means our final position when we get to the highest point on the ramp is going to be 24, right? 0 plus 24. All right, so I think we know everything we need to plot all this. So let's do it. Let me clear up my board here. Oh, oh no. No, well, darn it. There we go. That was a lot of work. Okay, so here we go. We got 10 seconds again. So 0, 2, 4, 6, 8, 10. I think I didn't label my axes on the last one, did I? Make sure you do that. No. Sorry if there's a loud noise. My microphone just fell. I don't know what just happened with that 8 there. All right, so let's see. My velocity needs to hit everything between 12 and negative 12, right? So we'll go 0. What do we want to do? Go by 3s. So we'll make this one 6 and make this 12. Down here we'll have negative 6 and negative 12. So for chunk 2, my velocity stays, or for chunk 1 rather, my velocity stays at 12 for 2 seconds. I need to calibrate the board. And then from there, the velocity decreases to negative 12. That takes 8 seconds. But please remember, 2 seconds have already passed. So here's my 8 seconds. So it's going to go. There we go. Start with this little blip here. All right, so there's my velocity time graph. And then my acceleration graph, well, my acceleration starts at 0 for 2 seconds. I'm not labeling my axes here in the interest of time. And then the acceleration dips down to negative 3 for the rest of the graph. Oops, I should have done that. Holy, I guess it doesn't matter. It's both. Okay, so label our axes, acceleration, meters per second squared. And here's negative 3. This was velocity in meters per second. Okay. Now over here we got to do our position in meters. So our position goes to everything from negative 24 to positive 24. So put 0 at the middle, and then let's go down. We need to get down to 24 by down here. So let's just go by 5s, I guess. So we'll call this negative 10, negative 20. That's a negative sign. And then negative 25 is at the bottom. And then up the top, we're going to have positive 25. You can fill in your numbers. Okay, so here's what we know. In chunk 1, our velocity is constant. We went from a position of negative 24 to a position of 0. So my position needs to start at negative 24, and after 2 seconds, it needs to be 0. A straight line, because the velocity is constant. It's the worst straight line ever. All right. Then in chunk 2, there's the 4 seconds during which it rolled up the hill. And at the end of those 4 seconds, it got to a position of 24. So we're going to start here at the bottom of the ramp. And then 4 seconds later, so I'm going to go over to 6, my position was 24. Right? So that's that. But then it rolls back down the hill, and we know that for the whole chunk 2, we have to end up back at 0. So we're actually doing this, going up to here, and then coming back down to 0 after 10 seconds. Okay, so there is your graph. All right, I hope that was helpful. I know a lot of you were out today for a field trip, so there you go.